What if the most brilliant breakthroughs in space exploration began not with applause, but with laughter? For generations, some of the boldest ideas for reaching the stars were dismissed as fantasy, too wild, too expensive, or just too strange to ever be taken seriously. Yet time and again, history has shown us that today's science fiction has a funny way of becoming tomorrow's science fact. Think about it. Not long ago, the idea of reusable rockets sounded like something out of a comic book. Now they're landing themselves back on Earth, changing everything we thought we knew about accessing space. It's a pattern as old as innovation itself. The visionaries who see farther are often first met with skepticism, only to be vindicated by the relentless march of discovery. We're about to embark on a journey through 24 of the most unusual space concepts that were once rejected, ideas that seemed absurd in their time, but are now stirring serious conversations among scientists, engineers, and dreamers. These aren't just far-off theories. Many are already being tested, prototyped, and reimagined with technologies we simply didn't have before. From solar sails that harness the gentle push of photons to space elevators that could one day carry us orbitward without a single rocket blast, what was once laughed out of the room is now being sketched onto whiteboards at NASA and private aerospace firms alike. This is the story of human imagination refusing to be boxed in of concepts that dared to challenge the possible and are now closer than ever to reshaping our future. So why do these ideas matter now more than ever? Because we stand at a crossroads, a moment when ambition and ingenuity are converging in ways that felt unthinkable just decades ago. The problems we face in space, how to travel farther, how to live sustainably beyond Earth, how to reach other worlds, demand solutions that are as radical as they are revolutionary. This video isn't just a tour of fascinating what-ifs. It's an invitation to witness the rebirth of ideas that could define the next chapter of humanity's journey into the cosmos. You'll discover why they were initially scorned, how science is breathing new life into them, and what it might mean for all of us when the impossible slowly, stubbornly becomes possible. Let's begin. History offers us a powerful lens through which to view today's most ambitious space concepts, and the pattern is strikingly consistent. The very foundations of modern rocketry were built upon ideas that were, at their inception, dismissed as the fanciful dreams of unserious minds. Consider Konstantin Tsiolkovsky, a Russian schoolteacher working in near isolation in the late 19th century. While he was meticulously calculating the mathematics of spaceflight and proposing the use of liquid propellants and multi-stage rockets, the very blueprints for how we reach orbit today, his work was largely ignored by the scientific establishment of his time. He was a voice in the wilderness, sketching out a future that seemed too distant, too abstract to be taken seriously. Across the ocean, Robert Goddard faced a similar wall of skepticism. After publishing his seminal work, A Method of Reaching Extreme Altitudes, which detailed the principles of liquid-fueled rockets and even suggested a rocket could one day reach the moon, he was met not with acclaim but with public mockery. A 1920 New York Times editorial famously scoffed at his ideas, asserting that a rocket could not function in the vacuum of space because it would have no air to push against, a fundamental misunderstanding of Newton's third law of motion that the newspaper wouldn't officially retract until after the Apollo 11 moon landing, nearly 50 years later. Goddard's response was to retreat from public scrutiny, conducting his pioneering experiments in the deserts of New Mexico, his work shielded from ridicule but also from the broader recognition it deserved during his lifetime. This resistance wasn't merely a matter of scientific debate. It was deeply rooted in the constraints of the era. The technological hurdles were immense. The materials, guidance systems, and propulsion methods needed to realize these visions simply didn't exist yet, making the concepts appear more like science fiction than actionable engineering. Furthermore, funding was a perpetual obstacle. Convincing governments or private patrons to invest vast sums in what was perceived as a fantastical pursuit required a leap of faith that few were willing to take. There was also an element of sheer conservatism within scientific institutions, a reluctance to depart from established paradigms and entertain ideas that disrupted conventional wisdom. Yet, the perseverance of these early pioneers ultimately laid the groundwork for every space achievement that followed. The multi-stage rockets Tsiolkovsky theorized became the key to escaping Earth's gravity. The liquid-fueled engines Goddard painstakingly tested are the direct ancestors of those that power every launch today. Their stories teach us a vital lesson about the nature of innovation. Progress is rarely a straight line from acceptance to achievement. More often, it is a winding path that begins with an idea so radical it can only be met with dismissal. It is the courage to challenge the status quo, to endure that initial laughter and skepticism, that ultimately paves the way for the breakthroughs that redefine what is possible. This historical context isn't just a record of past mistakes. It's a crucial framework for understanding why the unconventional ideas we'll explore next, which may seem equally far-fetched today, deserve our serious attention and open-minded curiosity. Now, let's turn our attention to one of the most elegant and poetic concepts in our cosmic toolkit, one that transforms light itself into motion, the solar sail. The core principle feels almost like magic, yet it is firmly grounded in the sober laws of physics. It begins with a simple, profound truth: light, though it has no mass, carries momentum. When photons, the particles of light, strike a surface, they impart a tiny, almost imperceptible push. For a spacecraft equipped with a vast, ultra-thin, and incredibly reflective sail, this constant rain of sunlight adds up to a continuous Chinese letter acceleration. There are no roaring engines, no burning fuel, just the silent, relentless pressure of starlight, a gentle cosmic breeze waiting to be harnessed. This vision is far from new. Its seeds were first planted in the 17th century by the astronomer Johannes Kepler, who observed that the tails of comets always pointed away from the sun and wondered if that same solar force could one day propel vessels through the void. But for centuries, it remained a beautiful thought experiment, dismissed by practical minds because the force involved is so incredibly faint. We're talking about the weight of a paperclip resting on your hand, a force seemingly useless for moving anything substantial. The overwhelming skepticism argued that building a sail large enough and lightweight enough to catch this ethereal wind was an engineering impossibility, a fantasy best left to the pages of science fiction novels. The modern champion who brought this idea back into the scientific mainstream was the beloved astronomer Carl Sagan. In the 1970s, he spoke of solar sailing with contagious passion on shows like The Tonight Show, presenting it not as a far-off dream but as a tangible possibility. He envisioned a regatta of light sails racing to Halley's Comet, capturing the public's imagination. Yet, even with Sagan's eloquent advocacy, the technological and material science hurdles remained immense. The concept was still largely greeted with polite skepticism from agencies focused on the brute force of chemical rockets. The turning point, as with so many rejected ideas, arrived with the quiet, relentless march of technological progress. The development of new materials, specifically ultra-lightweight polymers thinner than a human hair and composites that could be unfurled in the harsh environment of space, finally made the construction of a viable sail possible. The proof arrived in the last decade, not once but twice, transforming theory into triumphant reality. Japan's Ikaro's mission became the first spacecraft to successfully demonstrate solar sail propulsion in interplanetary space, cruising past Venus powered by nothing but sunlight. Then the Planetary Society, an organization co-founded by Carl Sagan himself, launched its Light Sail 2 mission. This crowd-funded spacecraft, no larger than a loaf of bread, spent months raising its orbit around Earth using only the pressure of photons on its silvery sail, a breathtaking validation of a concept decades in the making. This successful demonstration shatters old limitations and opens a new chapter for exploration. The most profound advantage of a solar sail is its sustainability. It requires zero fuel. This means a mission duration is not limited by propellant tanks but by the longevity of its components, allowing for truly long-duration voyages. Imagine a fleet of these craft stationed closer to the Sun, using the more intense sunlight to achieve high speeds before sailing onto the outer planets, acting as perpetual weather monitors or communications relays. Even more ambitious concepts involve targeting powerful ground-based lasers at the sails of tiny, wafer-sized probes, potentially accelerating them to a significant fraction of the speed of light for a flyby mission to the nearest stars within a human lifetime. The success of the solar sail does more than just prove a propulsion method. It fundamentally changes our relationship with the cosmos, suggesting that the energy for our journeys is already flowing all around us, if only we are clever enough to reach out and catch it. If the solar sail represents a way to glide on the cosmic winds, then our next concept reimagines the very architecture of ascent itself, proposing not a rocket but a railway to the stars. Envision a cable impossibly strong and breathtakingly long, anchored to the Earth's surface at one end and tethered to a counterweight far beyond geostationary orbit at the other. This is the space elevator, a structure that would quite literally provide a lift into space, transforming a perilous, explosive rocket ride into a serene, steady climb. The principle is one of simple, elegant balance, harnessing the centrifugal force of the Earth's rotation to keep the cable taut and stable, like a ball on a string swung around your head. A climber vehicle, powered remotely, would then traverse this tether, carrying cargo and eventually people into orbit for a fraction of the energy cost of a conventional launch. The genesis of this audacious idea is a testament to its enduring appeal. It was first seriously proposed by the same Russian pioneer we met earlier, Konstantin Tsiolkovsky, who in 1895 looked at the Eiffel Tower and imagined a celestial castle at the end of a similar structure reaching into the sky. The concept was later popularized and brought to the global consciousness by the visionary science fiction author Arthur C. Clarke in his 1979 novel, The Fountains of Paradise. For decades, it remained firmly in the realm of fiction because the single greatest obstacle was, and for a long time seemed to be, insurmountable: the material science. The tensile strength required for a cable over 22,000 miles long is almost beyond comprehension. It would need to support its own immense weight without snapping under the incredible stresses of gravity, wind, and orbital forces. For most of the 20th century, no known material, not steel, not titanium, not any alloy, came even remotely close to meeting this requirement. The idea was therefore dismissed by engineers as a beautiful but fundamentally impossible dream. The tide of opinion began to turn not with a grand announcement, but with a microscopic discovery: carbon nanotubes. This revolutionary material, essentially sheets of carbon atoms rolled into tubes a nanometer in diameter, possesses a theoretical tensile strength orders of magnitude greater than steel at a fraction of the weight. Suddenly, the impossible equation of the space elevator had a potential variable. Research into carbon nanotubes and their two-dimensional cousin, graphene, ignited a new wave of serious scientific inquiry. While manufacturing flawless, macroscopic strands of this material remains a monumental technical challenge, its existence proves that the physics itself is not forbidden. The dream is no longer a question of if it is possible according to the laws of nature, but when our engineering can catch up to the theory. This shift from fantasy to feasible project is best evidenced by the serious investment from major institutions. The Japanese construction giant Obayashi Corporation, known for building the Tokyo Skytree, has publicly announced its ambition to construct a space elevator by the year 2050. Their plan involves using carbon nanotube technology to build a 96,000-kilometer cable with robotic climbers transporting passengers and cargo to a sprawling orbital station. While the timeline is ambitious, the very fact that a reputable multinational corporation is dedicating resources to its development signals a profound change in perception. NASA and other space agencies have also funded numerous studies and competitions, such as the Elevator 2010 Challenge, encouraging innovators to tackle the problems of power beaming and climber design. The payoff for succeeding would be nothing short of a second space revolution. By eliminating the need for explosive chemical propellants to achieve orbit, a space elevator could reduce the cost of launching material from thousands of dollars per pound to mere tens of dollars. This would democratize access to space in an unprecedented way, enabling the construction of vast solar power satellites, sprawling space colonies, and serving as the starting point for deeper space missions that are assembled and launched from outside Earth's gravity well. The elevator wouldn't just be a transportation method, it would become the foundational pillar of a true spacefaring civilization, a permanent bridge between our world and the infinite potential above it. It stands as one of the most powerful examples of an idea that was once a symbol of scientific hubris, now patiently waiting for our technology to rise to meet its grand ambition. But if a space elevator represents a single, fixed tether to the heavens, then the concept of an orbital ring envisions something far grander and more dynamic, a continuous, artificial structure encircling the entire planet itself. Imagine a slender ring, not much wider than a highway, spinning at an incredible velocity high above the Earth, held aloft not by rockets but by the pure physics of momentum and magnetic force. This isn't science fiction, it's a serious engineering proposal that redefines our relationship with orbit, transforming it from a destination we briefly visit into a permanent, accessible realm we can actively inhabit and utilize. The modern architect of this breathtaking vision was the British engineer and futurist Paul Birch, who in the 1980s meticulously detailed the concept in a series of papers. His design was staggering in its ambition. The core idea involves a massive, rotating ring of cable positioned just above the atmosphere. Because this ring would be moving faster than orbital velocity, it would naturally want to fly outward into space. To counter this, it would be sheathed in a non-rotating sheath or housing that is magnetically levitated above the ring. This stationary sheath becomes the stable platform, a circular road in the sky upon which we could build launch facilities, solar power stations, factories, or even entire cities, all permanently stationed in low Earth orbit without needing to constantly fight gravity with thrusters. Unsurprisingly, the initial reaction from the aerospace community was a mixture of awe and outright dismissal. The scale of the undertaking was, and still is, almost incomprehensible. Constructing a structure that would need to be tens of thousands of miles in circumference presents logistical and material challenges that dwarf even the largest terrestrial projects. The critics' arguments were powerful and, at the time, entirely valid. Where would we get the millions of tons of material? How would we assemble it in space? Could any material known to humanity possibly withstand the titanic stresses involved without shattering? And perhaps the most damning question of all, who would possibly fund such a mega-project with costs that could easily eclipse the gross domestic product of entire nations? For decades, the orbital ring remained a fascinating thought experiment discussed in the corners of futurist conferences, but never on the main stage of space agency planning. The revival of this idea is a direct result of two converging forces, necessity and capability. The necessity is clearer now than ever before. Our planet's orbit is becoming increasingly crowded and economically vital. We need more stable, permanent infrastructure to manage space traffic, service satellites, construct large spacecraft for missions to Mars, and tap into the virtually limitless energy of the Sun. The economic and environmental case for beaming clean solar power directly to Earth from orbit grows stronger with each passing year. An orbital ring would be the ultimate foundation for all of this activity, a permanent foothold that makes every subsequent space endeavor easier and cheaper. On the capability side, while the challenges remain immense, they are no longer purely theoretical. The private space industry, led by companies dedicated to drastically reducing launch costs, is already working on the first piece of the puzzle: affordable access to orbit. Reusable rockets are the initial step to bringing down the price of shipping the vast quantities of material needed. Furthermore, the nascent field of in-space manufacturing and resource utilization suggests we may not need to launch everything from Earth. We could instead harvest materials from the Moon or asteroids, processing and constructing the ring itself in space, bypassing Earth's gravity well entirely. Advancements in materials science, particularly with high-strength carbon composites and active magnetic stabilization systems, provide a plausible, if distant, path to solving the structural integrity problems that once seemed impossible. The true genius of Paul Birch's orbital ring concept is its scalability. We wouldn't need to build the entire ring at once. We could start with a small demonstration loop, proving the technology and its economics. This initial segment could itself function as an unparalleled spaceport, slinging payloads to the Moon and beyond with minimal energy. From there, the ring could be gradually extended piece by piece, eventually forming a complete circle around our planet. This wouldn't just be a transportation system. It would become the backbone of a space-based industrial revolution, a constant reminder of human ingenuity literally surrounding our world. It stands as a testament to an idea so audacious it was once rejected out of hand, yet so powerful that it continues to inspire engineers to draw up the blueprints for humanity's next great architectural marvel. While the orbital ring reimagines our infrastructure in space, another concept asks a more fundamental question. What if we stopped bringing everything with us from Earth and started sourcing what we need from the cosmos itself? This is the promise of asteroid mining, a vision that transforms these wandering space rocks from passive celestial objects into active, invaluable resource depots. The core idea is as logical as it is revolutionary. After all, everything we have ever built, launched, or used, every ounce of metal, every drop of fuel, every resource consumed, was originally mined from our own planet. But Earth's resources are finite, and lifting them out of our planet's deep gravity well is phenomenally expensive. Asteroids, by contrast, are rich in the very materials we need to explore and thrive in space, and they possess virtually no gravity, making departure and transport infinitely easier. For decades, this notion was the exclusive domain of science fiction writers and a handful of far-sighted scientists. the practical objections were overwhelming and, at the time, entirely reasonable. The technological hurdles seemed insurmountable. How do you rendezvous with a tumbling rock moving at thousands of miles per hour? How do you anchor a mining apparatus to a surface with almost no gravity? How do you process raw ore in the airless, extreme temperature vacuum of space? And perhaps the most damning question of all, even if you could do it, how could it possibly be cheaper than just digging another mine here on Earth? The exorbitant projected costs and the sheer audacity of the engineering required led most to dismiss asteroid mining as a fantasy, a concept that would remain centuries out of reach. The turning point for this rejected idea came from a confluence of new discoveries and entrepreneurial ambition. First, our astronomical surveys revealed that many asteroids are not just barren rocks. A significant number, particularly carbonaceous chondrites, are treasure troves of water ice, locked away within their structures. This water is far more valuable than gold in space. It can be split into hydrogen and oxygen to create breathable air and, most importantly, rocket propellant. The realization that we could essentially mine the gas stations for our interplanetary journeys fundamentally changed the economic equation. Furthermore, other asteroids, the metallic M-types, are believed to contain vast quantities of platinum group metals, iron, nickel, and cobalt materials crucial for both in-space construction and high-tech industries on Earth. This new data provided the catalyst for a bold new wave of commercial space ventures. Companies like Planetary Resources and Deep Space Industries emerged in the early 2010s, not as think tanks, but as actual mining companies whose quarry just happened to be in space. Their business plans were serious, backed by major investors and featuring phased approaches. The first step wasn't to launch giant excavators. It was to develop and deploy a fleet of low-cost, miniature prospector spacecraft interplanetary drones designed to identify, rendezvous with, and analyze the most promising near-Earth asteroids, assessing their composition and value before a single mining tool was ever built. While the path has been challenging, with these pioneers facing financial hurdles, their work has irrevocably shifted the conversation. The technology they helped pioneer is now being pursued by a new generation of companies and has garnered serious interest and funding from space agencies like NASA. The space agencies' OSIRIS-REx and Psyche missions are, in essence, government-funded prospecting missions, proving the techniques needed to reach, study, and extract material from asteroids. The once laughable idea of off-world resources is now a core pillar of NASA's Artemis program, which plans to use water ice mined from the Moon and eventually asteroids to create a sustainable lunar economy. This institutional adoption signals a profound shift. Asteroid mining is no longer a question of if, but when. The promise is a future where space missions refuel at orbiting depots supplied by robotic miners, where massive space habitats are constructed from metals forged in the zero gravity of the asteroid belt, and where humanity's expansion into the solar system is powered not by what we take from Earth, but by what we find and use along the way. This pursuit of reshaping entire worlds brings us to perhaps the most ambitious and philosophically charged concept of all, terraforming. This is the grand endeavor of taking a barren, alien planet and deliberately altering its atmosphere, temperature, and ecology to make it habitable for earthly life. It's planetary engineering on the ultimate scale, a process that would transform a cold, radiation-scorched desert like Mars into a world with blue skies, flowing water, and a breathable atmosphere, a second home for humanity. For generations, this idea lived almost exclusively in the pages of science fiction, masterfully explored by authors like Kim Stanley Robinson in his seminal Mars trilogy. where he depicted the immense technological, political, and ethical drama of making Mars live. In the real world, the concept was largely dismissed as the height of ecological hubris, a fantastical dream that ignored the sheer, staggering scale of energy and time required to change the face of an entire world. The engineering challenges were so monumental and the potential for unintended consequences so vast that it seemed less like a future project and more like a mythology. What has shifted this idea from the realm of pure fantasy into a subject of legitimate scientific workshops and NASA-funded research is a sobering, ironic twist: our accelerating mastery over our own planet's climate. The same technologies and atmospheric models we are developing to combat human-induced climate change on Earth are providing the foundational tools and knowledge required to even contemplate inducing climate change on another planet. We are, in effect, becoming planetary-scale engineers by necessity at home, which gives us the first glimpse of how we might one day perform that role elsewhere. Furthermore, with multiple space agencies and private entities now developing concrete, near-term plans for a sustained human presence on Mars, the long-term question of how to make that presence truly sustainable, rather than living perpetually in sealed habitats, naturally leads back to these grander visions of transformation. The proposed methods for terraforming Mars read like a list of epic megaprojects, each more astounding than the last. One of the most discussed strategies involves deliberately triggering a runaway greenhouse effect, the very process we are trying to avert on Earth. This could be achieved by releasing powerful greenhouse gases, known as super greenhouse gases, into the Martian atmosphere. These synthetic compounds, potentially manufactured on site by automated factories, would be thousands of times more effective at trapping solar heat than carbon dioxide. Their purpose would be to jump-start the warming process, melting the vast reservoirs of water ice and frozen carbon dioxide trapped at the poles. As these ices sublimate into the atmosphere, they would release more CO2, a greenhouse gas itself, thickening the atmosphere and trapping even more heat in a powerful positive feedback loop. This thickening atmosphere would serve two critical functions. It would increase surface pressure to a point where liquid water could stably exist without instantly boiling away, and it would provide a crucial shield against harmful solar and cosmic radiation. Other proposals are even more breathtaking in their audacity. One involves deploying giant, ultra-thin mirrors into orbit around Mars. These solar sails, measured in square miles, would be strategically positioned to reflect and focus additional sunlight onto the polar ice caps, artificially accelerating their melting to thicken the atmosphere. Another concept suggests redirecting small, water-rich asteroids or comets from the outer solar system on a collision course with Mars. The impacts would deliver vast quantities of essential volatiles, water, ammonia, and methane directly to the planet, simultaneously contributing to its atmosphere and hydrosphere in dramatic cataclysmic events. Yet, for all the fascinating physics and emerging technological plausibility, terraforming forces us to confront a universe of profound ethical questions that are as complex as the engineering challenges. If microbial life exists on Mars, dormant deep underground or in shielded aquifers, do we have the right to extinguish it or irrevocably alter its environment in our quest for a new home? Would we be acting as stewards of life, spreading a precious biological phenomenon through the solar system, or as an invasive species, imposing our Earth-centric template on a world that has its own ancient story to tell? The process itself would take centuries, if not millennia, raising questions about the commitment and responsibility we would owe to countless future generations who would be born into a project they did not start. Terraforming is more than a technical blueprint. It is the ultimate expression of humanity's desire to not just visit space, but to truly live within it, to imprint our legacy upon the cosmos and, in doing so, confront the immense weight of that responsibility. But what if the most powerful solution to our planet's greatest challenge wasn't built on Earth at all, but constructed in the endless sunshine just beyond our atmosphere? This is the promise of space-based solar power, a concept as elegant as it is ambitious. Imagine massive satellites, each with solar arrays spanning several square miles, placed in a high orbit where the sun never sets. Unlike ground-based solar farms that are shackled by the cycle of day and night and the veil of clouds, these orbital power plants would bask in uninterrupted sunlight 24 hours a day. They would convert this immense, constant energy into microwaves or precisely targeted lasers, beaming it wirelessly down to receiving stations on Earth called rectennas, which would then convert it back into electricity and feed it directly into our power grids. It's a closed-loop system that treats our planet not as a power generator, but as a power receiver, tapping into a stream of clean energy from the ultimate source. The visionary behind this idea was Dr. Peter Glaser, who first patented the concept in 1968. At a time when the world was just beginning to grasp the potential of solar power on Earth, Glaser was already looking skyward, proposing a solution of truly cosmic proportions. Yet for decades, his brilliant proposal was met with overwhelming skepticism and filed away as an impractical dream. The criticisms were formidable and, for its time, entirely valid. The estimated cost of launching the thousands of tons of material required to build such a constellation of satellites was astronomical, far exceeding any conceivable economic return. The technical hurdles were equally daunting. Could a microwave beam be transmitted over such a vast distance with enough accuracy to hit a receiving station without dangerous dispersion? Could the system be made efficient enough to justify the energy lost in the multiple conversion steps? To the engineers and economists of the 1970s and 80s, the answer was a resounding no, and the concept was shelved as a fascinating but ultimately unworkable thought experiment. The revival of space-based solar power is a story of necessity finally aligning with possibility. The driving force is the urgent, global need to transition away from fossil fuels and combat climate change. This existential threat has forced us to re-evaluate every potential source of clean energy, no matter how ambitious. Simultaneously, the technological landscape has transformed in ways that directly address the old objections. The single greatest barrier, launch cost, is being dismantled by the rise of reusable rockets from companies like SpaceX, which are driving the price of sending payloads to orbit down by orders of magnitude. In space construction and robotic assembly, technologies being actively developed for other orbital infrastructure projects promise to further reduce the logistical nightmare of building such large structures. Perhaps most crucially, the core technology of wireless power transmission has moved from the realm of theory to demonstrable fact. The Japanese space agency JAXA has been a pioneer in this field, successfully transmitting power via microwaves over significant distances. In a landmark achievement, researchers at Caltech recently launched a prototype called the Space Solar Power Demonstrator. One of its key instruments, Maple, successfully demonstrated the ability to beam detectable power from orbit to a receiver on the roof of a campus laboratory in Pasadena. This wasn't just a laboratory experiment. It was a proof of concept conducted in the harsh environment of space, proving that the fundamental physics of targeted energy transfer works exactly as Peter Glaser predicted over half a century ago. The implications of perfecting this technology are nothing short of revolutionary. A single large-scale solar power satellite could generate a consistent gigawatt of power comparable to a major nuclear power plant, but without any radioactive waste, carbon emissions, or massive land use. A network of these stations could provide a baseload supply of clean energy that is completely immune to terrestrial weather and the day-night cycle, something that ground-based renewables like wind and solar still struggle with. This isn't just about powering homes, it's about fueling a global industrial civilization without poisoning the planet. It could provide the clean, abundant electricity needed for carbon capture technologies, for powering a global fleet of electric vehicles, and for enabling developing nations to grow their economies without following the dirty energy path of the past. Space-based solar power represents the ultimate convergence of our spacefaring ambitions with our terrestrial needs, turning the void of space into a utility that powers and preserves the world below. Now we arrive at a concept so audacious, so fundamentally explosive, that it stands apart even in this list of radical ideas: nuclear pulse propulsion. Forget chemical rockets or gentle solar sails. This is a technology that proposes to ride a continuous series of nuclear detonations across the solar system and beyond. The principle is as shockingly simple as it is powerful. Imagine a massive, heavily shielded spacecraft with a gigantic pusher plate attached to its stern by a robust shock absorption system. Behind this vessel, a device would eject a nuclear bomb, not a weapon, but a precisely engineered propulsive charge. The bomb detonates, and the plasma fireball slams into the pusher plate. The spacecraft, cushioned by its absorbers, is hurled forward by the immense force of the blast. Then, another bomb is ejected and detonated, and another, creating a rhythmic, apocalyptic drumbeat of explosions that pushes the ship to velocities unimaginable with any conventional engine. This was the brilliant, terrifying brainchild of Project Orion, a secretive study conducted in the late 1950s and early 60s by a team of top-tier scientists and mathematicians, including the legendary Freeman Dyson. Their calculations were staggering. A full-scale Orion spacecraft could, in theory, reach Saturn and back in just 7 months, or make a round trip to Mars in a matter of weeks. The larger the design, the better it worked. Interplanetary arc ships the size of small cities were considered feasible, capable of carrying entire colonies to the outer planets. The team had such confidence in their physics that they built and successfully flew small-scale demonstrators using conventional chemical explosives, proving that the pulse principle was sound. For a brief, thrilling moment, it seemed humanity had stumbled upon the key to the entire solar system. Yet, despite its breathtaking potential, Project Orion was not merely shelved, it was emphatically cancelled and buried. The reasons had nothing to do with the laws of physics and everything to do with the realities of Earth. The 1960s were the peak of the Cold War and the height of global anxiety over nuclear weapons. The idea of lofting thousands of nuclear warheads into space, even for peaceful purposes, was a political and diplomatic impossibility. The Partial Test Ban Treaty of 1963, which prohibited nuclear explosions in the atmosphere, underwater, and in outer space, effectively slammed the door on Orion's specific approach. Beyond the politics were serious environmental and safety concerns. The fallout from launching such a vessel from Earth's surface was deemed unacceptable, and the public perception of a nuclear bomb-powered starship was understandably a public relations nightmare. The dream of riding explosions to the stars collided with the sobering fear of nuclear annihilation and was utterly defeated. But a dream this powerful has a way of resurfacing. Today, in an era where the goalposts of exploration have moved from the planets to the stars themselves, nuclear pulse propulsion is experiencing a quiet but serious renaissance. The new driving force is the interstellar question. Conventional propulsion, even advanced ion drives, would take tens of thousands of years to reach the nearest star system, Alpha Centauri. Generation ships are one theoretical solution. but the prospect of a mission that takes less than a single human lifetime is far more compelling. Modern reconsiderations, often called Project Orion's grandchildren, aim to solve the original concept's fatal flaws. One promising direction is to use fusion-based pulses instead of fission bombs. Cleaner, more efficient fusion micro-explosions, potentially initiated by lasers or particle beams, could provide the tremendous thrust without the radioactive legacy. Another key innovation is the proposal to assemble and launch these vessels from orbit, never risking a nuclear launch from Earth's surface. The most advanced modern incarnation of this idea is known as Project Daedalus, a detailed technical study conducted by the British Interplanetary Society in the 1970s. This unmanned probe design used pellets of deuterium and helium-3, ignited by electron beams in a reaction chamber, to create a continuous fusion pulse, accelerating a 450-ton payload to an astonishing 12% of the speed of light. Such a vessel could reach Barnard's star, nearly 6 light-years away, in about 50 years. While the engineering for Daedalus remains far beyond our current grasp, it serves as a crucial blueprint, a proof of concept that demonstrates that interstellar travel is not forbidden by physics, only by our current level of technological maturity. This concept forces upon us the most profound ethical calculation in all of space exploration. It demands that we weigh our boundless ambition to reach out and touch other worlds against our immense responsibility to protect our own. Is the prize of becoming an interstellar species worth the risk of normalizing the very technology that threatens our existence? Can we develop and contain such an awesome power solely for peaceful exploration? Nuclear pulse propulsion is more than an engineering challenge. It is a moral crucible. It tests our ability to harness the fire of the sun for creation rather than destruction, asking if we are wise enough to finally turn our most terrible invention into our greatest engine of discovery. Yet as we venture outward, we must confront a silent, insidious threat that no amount of radiation shielding can fully block: the absence of gravity itself. For all the wonder of floating in microgravity, the human body is fundamentally designed for Earth's constant pull. Without it, our physiology begins to unravel. Astronauts on long-duration missions face severe muscle atrophy and skeletal deterioration, losing bone density at a rate comparable to osteoporosis. Fluids shift upward, causing vision-impairing pressure on the eyes and brains. The cardiovascular system weakens, and the immune system becomes less effective. These aren't temporary inconveniences. They are profound biological challenges that pose a fundamental limit to how long humans can live and work in space, threatening any dream of permanent settlement beyond Earth. The solution to this existential problem is as elegant as it is colossal, and its roots stretch back to the very dawn of the space age. The concept of artificial gravity through rotation was first seriously proposed by rocket pioneer Wernher von Braun. In the 1950s, he envisioned a colossal, wheel-shaped space station, spinning slowly to use centrifugal force to simulate gravity, pinning objects and people against the outer rim. This wasn't just a technical sketch. It was a complete reimagining of life in space, with decks oriented outward toward the stars and a hub for docking and zero-G work. It captured the public imagination, most famously realized in the iconic spinning space station from the film 2001: A Space Odyssey. Yet for decades, this vision remained firmly on the drawing board, dismissed by pragmatists as a fantastical solution to a problem we hadn't even fully encountered yet. The sheer scale and mass of such a structure made it seem impossibly expensive and complex compared to the simpler, smaller modules we were learning to launch and assemble. The true visionary who transformed this idea from a sci-fi trope into a serious engineering blueprint was physicist Gerard Kay. O'Neill. In the 1970s, he asked a simple, revolutionary question: is a planetary surface the right place for an expanding technological civilization? His answer was a resounding no. He and his students at Princeton University conducted detailed studies, culminating in designs for vast, free-floating space colonies that were breathtaking in their ambition. The most famous, the O'Neill cylinder, proposed two massive counter-rotating cylinders, each 20 miles long and 5 miles in diameter, rotating every 2 minutes to simulate Earth normal gravity on their inner surfaces. These would not be mere stations, they would be entire worlds. The inside of the cylinder would be landscaped with valleys, rivers, and towns, lit by massive mirrors that reflected sunlight in a natural day-night cycle. The Stanford Torus, another design from this era, envisioned a smaller, donut-shaped ring 1 mile in diameter, rotating to create gravity on its inner circumference, capable of housing 10,000 people in a self-sustaining environment. At the time, these designs were met with a mixture of fascination and outright dismissal. The criticism was not about the physics, which was sound, but about the overwhelming scale and perceived extravagance. Launching the millions of tons of material from Earth was economically unthinkable. The concept was shelved as a beautiful, utopian dream for a far distant future, while the space industry focused on the more immediate challenges of orbital mechanics and zero-G survival. What has spectacularly revived this rejected idea is a powerful one-two punch: newfound necessity and newfound capability. The necessity is our concrete ambition for long-duration missions. NASA Artemis program and plans for a sustained lunar presence, along with the goal of sending humans to Mars, a journey that could take over 6 months one way, have made solving the gravity problem an urgent medical priority. We can no longer ignore the biological clock ticking against our explorers. Simultaneously, the capability side of the equation is being rewritten by the private space sector. SpaceX's Starship, designed as a fully reusable super-heavy lift vehicle, promises to slash the cost of launching massive payloads into orbit. Its payload bay is large enough to carry segments of what would essentially be a Stanford Torus module. This changes the entire economic calculus, making the construction of large rotating structures not just plausible, but potentially cost-effective. We are already seeing the first tentative steps toward this future. NASA's planned Lunar Gateway Station will include elements that may be capable of demonstrating slow rotation to create partial gravity, a crucial testbed for understanding how much gravity is actually needed to maintain human health. Is Mars-level gravity at 38% of Earth's sufficient, or do we need a full 1G? These are questions we can only answer by building and experimenting with rotating habitats. The ultimate goal is no longer just survival in space, but true prosperity. An O'Neill cylinder would be more than a habitat. It would be an ark, a factory, and a farm. It could support vast agricultural lands growing food under controlled conditions, laboratories leveraging the pure vacuum and zero-G of its central axis, and industries that are impossible on Earth. It represents the moment humanity stops trying to endure the space environment and begins to recreate the one environment we truly need, carrying the gift of gravity with us wherever we choose to go, and in doing so, finally becoming a species at home among the stars. But if nuclear pulse propulsion represents the most explosive way to cross our solar system, the next concept offers a far more elegant and truly mind-bending path to the stars, one that doesn't merely push through space, but manipulates the very fabric of spacetime itself. This is the warp drive, a theoretical engine that would allow a spacecraft to effectively ride a wave of distorted spacetime, traveling faster than the speed of light without actually moving through local space at all. The principle, inspired by Einstein's theory of general relativity, is that mass and energy can warp the geometry of the universe. A warp drive would create a bubble of flat space-time around a ship, while contracting the space immediately in front of it and expanding the space behind it. In essence, the universe itself would move around the stationary spacecraft, sidestepping the universal speed limit that light travels at within space-time. It's not about going faster, it's about making the destination closer and the point of departure farther away. The modern architect of this astounding idea is Mexican physicist Miguel Alcubierre. In 1994, he published a groundbreaking paper that translated this science fiction staple into a rigorous mathematical framework, proving that such a drive was not forbidden by the equations of general relativity. For the scientific community, this was simultaneously a moment of awe and immediate dismissal. The problem was not the math, but the staggering physical requirement it revealed. To create the necessary curvature of space-time, Alcubierre's solution demanded the existence of a mysterious substance called exotic matter. This wouldn't be normal matter or even antimatter. It would need to possess something called negative energy density, effectively having negative mass. This exotic matter would be required to create the repulsive gravity needed to expand space-time behind the bubble. Since no such substance had ever been observed or created, and its properties seemed to violate known energy conditions, the warp drive was swiftly relegated to the shelf of fascinating but impossible ideas, a theoretical curiosity with no bridge to reality. What has reignited serious scientific interest in this once dismissed concept is a series of tantalizing breakthroughs in seemingly unrelated fields. The first glimmer of hope came from the strange world of quantum mechanics. The Casimir effect, a well-demonstrated quantum phenomenon, shows that the vacuum of space between two very close, uncharged metal plates can indeed exhibit a negative energy density, as it has less energy than the surrounding vacuum. While the amount of energy produced is infinitesimally small, it provides a crucial proof of principle that the quantum vacuum can behave in ways that align with the requirements for exotic matter. This discovery shifted the question from, "Is this possible?" to, "How could we possibly harness and amplify this effect?" Simultaneously, advancements in metamaterials, artificially engineered structures that can manipulate electromagnetic waves in ways not found in nature, have provided a tangible analog for how we might one day control space-time itself. Just as a metamaterial cloak can bend light around an object to render it invisible, the mathematics describing this process are eerily similar to the equations governing a warp bubble. Researchers have begun drawing direct parallels, suggesting that the principles of crafting a space-time metric might be explored first in a lab using microwave radiation and carefully designed metamaterials, a kind of warp drive in a tabletop experiment. This theoretical work has moved beyond mere speculation and into the realm of active, albeit preliminary, experimentation. The most prominent effort is happening at NASA EagleWorks Laboratories, a small, advanced propulsion research group led by scientist Harold White. Their work involves attempting to create and measure microscopic warp bubbles using a device called a White-Jude warp field interferometer. By applying intense electromagnetic fields to the fabric of spacetime, they hope to detect a tiny, telltale distortion that would confirm the underlying principles are not just mathematical but physically achievable. While the energy requirements for a full-scale drive remain astronomical, initially calculated to be equivalent to the mass energy of Jupiter, subsequent refinements by White and others suggest that by oscillating the warp bubble or changing its shape, those requirements could be lowered to something more akin to the mass of a small spacecraft. This doesn't mean we're building a starship tomorrow. but it transforms the concept from a mathematical fantasy into a distant yet conceivable engineering challenge. The warp drive represents the ultimate horizon of human ambition, the holy grail of interstellar exploration. It is a concept that dares us to dream beyond the limits of known physics, to envision a future where the galaxy is not a lonely, untouchable expanse, but a network of potential homes waiting to be visited. It promises not just faster travel, but a fundamental redefinition of our place in the cosmos. Where a journey to Alpha Centauri would take tens of thousands of years with conventional rockets, a warp-driven ship could make the trip in weeks or days from the perspective of those on board. This would transform humanity from a species tethered to its solar system into a truly galactic civilization, capable of exploration, communication, and connection on a scale that is currently the sole domain of our boldest science fiction. The pursuit of the warp drive is more than a technical challenge. It is a testament to our species' relentless curiosity, our refusal to accept boundaries, and our profound belief that no destination, no matter how distant, should forever remain out of reach. But if we seek a technology that offers the speed of a warp drive without needing to rewrite the laws of physics, we arrive at a concept that is startlingly direct. Why carry your engine with you when you can leave it at home? This is the radical proposition of laser propulsion, a system where the immense power source remains firmly on the ground or in orbit, and the spacecraft, a lightweight vessel, is pushed across the cosmos by a relentless beam of pure light. The principle builds beautifully upon the solar sail we discussed earlier, but supercharges it. Instead of relying on the gentle, diffuse push of sunlight, a laser propulsion system would focus a concentrated, high-energy beam onto a sail, delivering a force thousands of times more powerful and allowing for controlled, rapid acceleration to a significant fraction of the speed of light. The spacecraft itself becomes a simple, elegant vessel, little more than a sail, a chip, and a camera, unburdened by the weight of fuel or engines, free to ride a highway of photons to the stars. The visionary who first translated this sci-fi concept into hard physics was the brilliant physicist and science fiction author Robert L. Forward. Throughout the 1980s and 90s, he devised incredibly detailed proposals for laser-pushed light sails, outlining missions that could send probes to nearby stars within a human lifetime. His designs were marvels of engineering creativity, including ideas for a giant Fresnel lens placed beyond the orbit of Pluto to keep the laser beam focused over interstellar distances, and a double sail system that would allow the craft to decelerate upon reaching its destination. Yet for years, his work was met with profound skepticism. The challenges seemed utterly insurmountable. Critics pointed to the astronomical power requirements. You would need a laser array consuming the entire power output of a major nation just to get started. The precision required was equally daunting. Keeping a laser beam perfectly focused on a sail the size of a football field from billions of miles away was compared to threading a cosmic needle, while both the needle and the thread were moving at incredible speeds. The slightest miscalculation or jitter would mean missing the target entirely, losing the probe into the endless void. For a long time, laser propulsion was seen as a fascinating intellectual exercise, but one that belonged to a future centuries removed from our own. The dramatic shift that has brought this idea roaring back into the realm of serious scientific pursuit is a classic case of a paradigm shift in scale and miniaturization. The key insight was that we didn't need to start by launching giant, heavy probes. We could start small, incredibly small. This philosophy is the driving force behind Breakthrough Starshot, one of the most ambitious and audacious scientific initiatives of the 21st century. Backed by billionaire Yuri Milner and supported by a board that includes the late Stephen Hawking, Starshot's goal is to create a proof-of-concept mission to Alpha Centauri within a generation. Their plan is breathtaking in its elegance and ambition. Instead of a large spacecraft, they propose a fleet of gram-scale star chips, tiny wafers packed with miniaturized cameras, sensors, and communication equipment. Each of these nanocraft would be attached to a light sail only a few meters wide, made of an ultra-thin, highly reflective material like metamaterial. The ground-based infrastructure would be a phased array of gigawatt-powered lasers, a light beamer stretching for possibly a kilometer. By combining their power, this array would create a single, immensely powerful beam aimed at the sails. For a few minutes, this beam would push on the sails, accelerating the tiny probes to an unprecedented 20% of the speed of light. At that velocity, the 4.37 light-year journey to Alpha Centauri would take just about 20 years, with another 4+ years for the data to stream back to Earth. The challenges remain immense, protecting the nanocraft from interstellar dust, achieving the necessary laser coherence, and developing the sail material to withstand the phenomenal power without vaporizing. But the project has moved beyond theory. Active research and development is underway, with teams testing prototype sail materials and working on the laser array technology. This single project has single-handedly transformed laser propulsion from a back-of-the-envelope calculation into a multidisciplinary global research effort, proving that the concept is no longer a fantasy, but a formidable engineering challenge we are actively beginning to tackle. The implications of perfecting this technology extend far beyond a one-time mission to our nearest stellar neighbor. Success would utterly revolutionize our entire approach to exploring our own solar system. Imagine a network of laser arrays in Earth orbit or on the lunar surface. We could dispatch small, cheap probes to any destination at incredible speeds. A mission to Mars could take days instead of months. A probe could be sent to intercept a newly discovered interstellar object like Oumuamua within a matter of weeks. We could have a constant stream of data from the cloud tops of Jupiter, the plumes of Enceladus, and the distant reaches of the Kuiper Belt, all enabled by this same laser highway. It would democratize deep space exploration, making it faster, cheaper, and more accessible than ever before. Laser propulsion represents the ultimate separation of the energy source from the vehicle, untethering our curiosity from the tyranny of the rocket equation and offering a tangible path to becoming a truly interstellar species, one light beam at a time. Yet for all the grandeur of engineering megastructures and breakthrough propulsion, the most intimate and profound challenge of living in space lies in recreating the delicate, invisible web of life that sustains us here on Earth. This brings us to the concept of biospheres, self-contained, self-sustaining ecosystems designed to function as a miniature version of our own planet, recycling air, water, and waste to support human life indefinitely without any input from the outside world. It is the ultimate test of our understanding of ecology, an attempt to bottle the genius of Earth's biosphere and carry it with us into the void. The vision is breathtaking, not just a sterile metal habitat, but a living, breathing world in miniature, complete with plants, microorganisms, and perhaps even insects or fish, all working in a closed loop to create a perpetual life support machine. The most famous and infamous attempt to realize this vision was Biosphere 2, a monumental experiment conducted in the Arizona desert in the early 1990s. This 3.14-acre sealed glass complex was designed to be a completely isolated microcosm of Earth's environments, housing a rainforest, an ocean, a desert, and agricultural land. 8 biospherians were sealed inside for 2 years, intending to live off the air, food, and water produced entirely within the structure. Initially, the project captured the world's imagination, hailed as a daring first step toward colonizing other planets. But the reality quickly proved far more complex and humbling than the optimistic forecasts. The carefully balanced atmosphere began to fail. Oxygen levels dropped to dangerously low levels, while carbon dioxide spiked to concentrations that would impair human cognitive function. Unanticipated explosions of soil microbes consumed the precious oxygen, and many of the pollinating insects went extinct, causing crop failures. The crew faced hunger and oxygen deprivation, forcing mission controllers to controversially pump oxygen into the facility from the outside, breaking the seal and, in the eyes of many critics, breaking the experiment. The project was widely declared a spectacular, costly failure, and for years, the very idea of a closed ecological life support system was tarnished, dismissed as an ecological pipe dream that underestimated the sublime complexity of nature. But a fascinating thing happened in the decades that followed. Rather than being a tombstone for the concept, Biosphere 2 became its most valuable textbook. The so-called failures were not actually failures of the core idea, but rather a brutal, accelerated education in systems ecology. Scientists realized that they hadn't failed to build a biosphere. They had simply learned how unimaginably complex a real biosphere truly is. The data gathered from those struggles became priceless. Researchers gained profound insights into the intricate dance between soil bacteria, plants, and atmospheric gases. They learned that concrete, a major building material inside the structure, was actively absorbing oxygen, a crucial lesson for future habitat design. They saw firsthand how difficult it is to achieve a stable balance in a young, immature ecosystem, a process that on Earth took billions of years of evolution. This hard-won knowledge did not kill the dream of biospheres. It provided the essential blueprint for making them work. This knowledge is now being directly applied to the most advanced life support systems in development for the Moon and Mars. Modern designs have moved away from the romantic idea of a perfectly balanced, fully biological system and toward a more pragmatic, hybrid approach known as a closed-loop or regenerative life support system. The heart of these systems is a sophisticated technological core that handles the immediate, critical tasks of air and water recycling with absolute reliability. This includes using electrolysis to split water into breathable oxygen and hydrogen, and employing Sabatier reactors to combine carbon dioxide from the air with hydrogen to create water and methane. Wrapping around this robust technological core is the biological layer, advanced hydroponic and aeroponic farms growing calorie-dense and nutrient-rich crops. These plants do more than just provide food. They become integral parts of the recycling system, absorbing carbon dioxide, producing oxygen, and helping to purify water through transpiration. Artificial intelligence and a network of thousands of sensors constantly monitor the atmosphere, water quality, and plant health, making micro-adjustments in real time to prevent the kind of imbalances that plagued Biosphere 2. It's a partnership between the brute force precision of engineering and the elegant, sustainable processes of biology. The payoff for perfecting this technology is nothing less than the achievement of true independence from Earth. A successful biosphere is the key to unlocking permanent settlement. It drastically reduces the staggering cost and risk of resupply missions. Instead of needing constant deliveries of water, air, and food, a colony would only need occasional shipments of spare parts and specialized goods. This transforms a space habitat from a precarious lifeboat entirely dependent on its home port into a self-reliant homestead capable of sustaining itself indefinitely. Beyond mere survival, a functioning biosphere provides immense psychological benefits for crews on long-duration missions, tending to living plants and being surrounded by greenery. A concept known as bioregenerative life support has been shown to significantly reduce stress and combat feelings of isolation and confinement. It's the difference between living in a sterile hotel room and living in a home with a garden. The biosphere concept, born from early ambition and tempered by humbling failure, is now evolving into the practical foundation for ensuring that humanity doesn't just visit space, but truly learns to live there, taking a vital piece of our living world with us. While we contemplate the incredible challenge of recreating Earth's biosphere in miniature, this ambition reaches its absolute zenith with the concept of the space ark, a generation ship conceived not as a mere habitat, but as a permanent traveling world. Envision a vessel of truly staggering proportions, a self-contained civilization designed to journey for centuries or even millennia between the stars. Its passengers would not be the crew that launched it. They would be the children, grandchildren, and great-grandchildren of those original pioneers, born into the journey, living their entire lives within the metal and glass confines of the Ark, with the ultimate mission of one day delivering humanity to a new home around a distant sun. This is not a mission measured in years, but in generations, representing the most profound long-term investment in the future of our species ever conceived. For most of the space age, this idea was relegated to the pages of epic science fiction, a thought experiment dismissed by practical minds due to a cascade of seemingly insurmountable hurdles. The psychological challenges alone are daunting. Could a society remain stable and purposeful when cut off from Earth, with the original mission fading into legend and the destination still dozens of generations away? The biological risks are equally severe. Maintaining a genetically healthy and diverse population over centuries within a closed system would require meticulous planning to avoid dangerous inbreeding or genetic drift. And then there are the technical nightmares, building a structure durable enough to withstand micrometeoroids and cosmic radiation for thousands of years, and creating a perfectly balanced, fail-proof ecological system that could not suffer a catastrophic collapse like Biosphere 2, with no possibility of outside rescue. The sheer scale of resources and energy required made the entire concept appear to be a utopian fantasy, a solution so complex it was worse than the problem it aimed to solve. The revival of the generation ship as a subject of serious scientific workshops and academic papers is driven by a sobering astronomical reality and a suite of emerging technologies. The reality is the vast, empty distance between stars, even with advanced propulsion, reaching a potentially habitable world like those orbiting Proxima Centauri or TRAPPIST-1 would likely take centuries. If we wish to send humans and not just robotic probes, a generation ship begins to look less like a fantasy and more like the only physically plausible option. The technological drivers making it seem less implausible are breakthroughs in several key fields. Advances in closed-loop life support learned from past failures provide a roadmap for those crucial sustainable ecosystems. Artificial intelligence and sophisticated automation could manage the ship's systems, act as a repository of all human knowledge, and even guide the society, helping to maintain cultural and mission stability across generations. Perhaps most intriguingly, progress in cryopreservation and suspended animation, while still in its infancy, offers a potential alternative path, not replacing the generation ship concept, but potentially shortening the subjective time of the journey for its inhabitants, turning a multi-century voyage into a long sleep. The most compelling modern iterations of this idea focus on feasibility through scale and redundancy. The concept is no longer a single, fragile ship, but a flotilla, a fleet of arks traveling together. This island-hopping model provides a critical safety net. If one vessel suffers an ecological or technical disaster, its population could potentially be evacuated to the others, ensuring the mission's survival. These ships would likely be constructed not on Earth, but in space, using materials harvested from the Moon or asteroids, their designs incorporating massive radiation shields of water or regolith and vast interior spaces spun to create artificial gravity. They would be more than ships, they would be ecosystems with forests, rivers, and farms under domed skies, designed to provide not just sustenance but a high quality of life for the generations born within them. Ultimately, the space arc forces a fundamental shift in human perspective. It demands that we plan on a timescale that dwarfs our own lifespans, investing in a future we will never see for the benefit of descendants we will never know. It is the ultimate expression of faith in the future and a powerful hedge against existential risk for humanity. By planting multiple seeds of civilization across the galaxy, we ensure that no single catastrophe, whether on Earth or befalling one arc, can ever extinguish the human story. The generation ship is the antithesis of a quick fix. It is a patient, enduring promise, a vessel carrying not just people, but the entire, unbroken thread of culture, knowledge, and life itself into the endless dark, ensuring that whatever happens, the light of consciousness will continue to burn. But what if the key to exploring the giant planets isn't a bigger engine, but a bigger net? This brings us to the brilliantly elegant concept of the magnetic sail, a propulsion system that turns a planet's own magnetic field into a brake pad. The principle is a masterclass in working with the cosmos instead of against it. Imagine a spacecraft deploying a massive loop of superconducting wire, perhaps dozens of kilometers across. When an electric current is run through this loop, it generates its own powerful magnetic field. As the craft then plunges into the magnetosphere of a giant planet like Jupiter, a realm dominated by its own immense, swirling magnetic field, the two fields interact. This creates a powerful drag force, effectively slowing the spacecraft down without it ever having to fire a traditional rocket engine or carry a single drop of braking propellant. It's a way to hitch a ride on the invisible magnetic highways that surround these gas giants. This ingenious idea was first seriously proposed by aerospace engineers Dana Andrews and Robert Zubrin in the 1990s. They saw it as the perfect solution to one of space travel's most fuel-intensive maneuvers, or orbital insertion. Slowing down enough to be captured by a planet's gravity requires a tremendous amount of energy, usually provided by a large, heavy engine burning at just the right moment. For missions to the distant outer planets, this means carrying all that braking fuel on the long journey out, drastically increasing the mission's mass and cost from the very start. The magnetic sail promised a way to offload that braking force onto the environment of the destination itself. Yet, for years, the concept was considered a clever theoretical exercise with little practical hope. The criticism was straightforward and seemed fatal. To generate a magnetic field strong enough to create meaningful drag against a planetary magnetosphere, the loop would need to be impractically large, and the superconducting materials required to carry such a massive current without resistance were, at the time, still confined to laboratory experiments and couldn't be deployed in the harsh, variable temperatures of space. The revival of the magnetic sail is a story of materials science once again catching up to visionary engineering. The breakthrough has been the rapid advancement in high-temperature superconductors. Unlike the early superconductors that required cooling to temperatures near absolute zero with expensive liquid helium, new ceramic and iron-based superconductors can operate at much higher, more manageable temperatures. This makes the prospect of building a large, lightweight superconducting coil that can be cooled and maintained in space infinitely more feasible. Researchers are now actively designing and testing prototypes of these coils, working on the intricate challenges of deploying such a large, fragile structure in microgravity and managing the current flow within it. What was once a paper concept is now a series of engineering problems with plausible solutions in sight. The potential applications for this technology are transformative, particularly for unlocking the outer solar system. A mission to Jupiter equipped with a magnetic sail could make its long journey out and then, upon arrival, simply deploy its loop and let the planet's monstrous magnetic field, the largest structure in the solar system after the Sun itself, do the work of slowing it down. This would allow for a much smaller, lighter spacecraft, as all the mass previously dedicated to braking fuel and engines could be reallocated to more scientific instruments or a longer mission duration. It makes multiple orbital tours of a planet's moons far more feasible, as the sail could potentially be used for repeated braking maneuvers. Looking even farther ahead, the concept extends to interstellar travel. A magnetic sail, or a related concept called a mag sail, could be used as a brake for an incoming starship. By interacting with the thin plasma present in interstellar space or the extended hydrogen envelope of a star system, it could provide a critical method of deceleration for a probe traveling at a fraction of the speed of light, solving the other half of the interstellar travel equation that concepts like laser propulsion struggle with. The true beauty of the magnetic sail lies in its philosophical elegance. It represents a shift from brute force conquest of space to a more nuanced, intelligent navigation of it. Instead of battling cosmic forces with overwhelming power, it seeks to understand and harness them, using the natural infrastructure of the solar system to our advantage. It turns a planet from a mere destination into an active participant in the journey, providing the means for its own exploration. This technology exemplifies a future where our voyages are defined not by the weight of the fuel we carry, but by the cleverness of the solutions we devise. While we explore ways to bend the fabric of space-time or build arcs for millennia-long journeys, another revolution is brewing in the realm of the infinitesimally small, promising to solve one of the most persistent problems in space exploration: the agonizing lag of communication across vast distances. This brings us to the enigmatic world of quantum communication, a concept that sounds like it's pulled from the pages of a physics fantasy novel. At its heart lies one of the most bizarre and counterintuitive phenomena in all of science: quantum entanglement. This is the spooky connection where two particles, like a pair of photons, are linked in such a way that the state of one instantly influences the state of its partner, no matter how many light years separate them. Measure one here, and its twin on the far side of the galaxy will respond in that very same instant, seemingly defying the universal speed limit set by the speed of light. For the better part of a century, this peculiar feature of quantum mechanics was a subject of intense philosophical debate and laboratory experiments, but it was widely dismissed as a tool for practical communication. The reasons for this skepticism were deeply rooted in the physics itself. The act of measuring a quantum particle fundamentally alters its state, a process called decoherence, which seemed to shatter any delicate entangled link the moment you tried to use it to send a message. Furthermore, the no-cloning theorem of quantum mechanics states that it's impossible to create an identical copy of an unknown quantum state, which appeared to rule out the possibility of amplifying a quantum signal like we do with classical radio waves, making it useless for long-distance transmission across the noisy depths of space. The scientific consensus was clear. While entanglement was a fascinating proof of the universe's weirdness, it was a dead end for building a functional communication system. The dramatic reversal of this dismissal is a story of bold engineering meeting profound theoretical insight. the critical breakthrough was the understanding that while entanglement itself couldn't be used to send information faster than light, a fact that preserves Einstein's cosmic speed limit, it could be used to create something even more valuable: perfectly secure keys for encryption. This is the foundation of quantum key distribution. Here's how it works. Two parties, let's call them Alice and Bob, share a pair of entangled photons. Alice measures her photon, which instantly randomizes the state of Bob's photon due to their entanglement. By comparing a subset of their measurements over a classical channel, like a radio wave, they can generate a secret cryptographic key that is known only to them. The magic is in the security. If an eavesdropper, Eve, tries to intercept and measure the photons in transit, her act of measurement will inevitably alter their quantum states, introducing errors that Alice and Bob can immediately detect. This means any attempt to spy on the communication is not just prevented, it is announced, guaranteeing the absolute privacy of the channel. This theoretical possibility was transformed into a stunning reality high above our heads. In 2016, China launched the pioneering Michus satellite, named after an ancient Chinese philosopher, dedicated to testing quantum communication on a global scale. The satellite acted as a master distributor of entangled photons, beaming them down to ground stations in China and Austria that were separated by over 4,600 miles. In a series of landmark experiments, Michus demonstrated the first intercontinental quantum secured video call and successfully distributed encryption keys between these two distant points, a feat impossible with ground-based fiber optics due to signal loss over such distances. The vacuum of space, it turned out, was the perfect medium for preserving these fragile quantum states over planetary scales, and a satellite could act as the essential relay node in a future quantum internet. The implications for space exploration are nothing short of transformative. For missions to the outer planets or beyond, communication delay is a crippling constraint. A command sent to a rover on Mars can take up to 20 minutes to arrive, and its response another 20 minutes to return. This makes real-time control impossible and turns delicate operations, like navigating difficult terrain, into a slow, painstaking process of sending instructions and waiting to see what happened. A quantum communication network with satellites around Mars or deeper space nodes could use entangled pairs to establish secure keys instantly. While the actual data itself would still travel at the speed of light, the ability to establish a perfectly secure, high-bandwidth channel in real time would revolutionize mission control. Scientists could pilot rovers as if they were there, experiencing the surface of another world with virtually no lag. For crewed missions, it would guarantee private, unhackable communication with Earth, a critical need for both operational security and the personal well-being of astronauts far from home. Looking even farther ahead, this technology paves the way for a truly interstellar internet. Imagine a future where we have probes around Alpha Centauri. By regularly shipping capsules of entangled particles, a process called quantum teleportation, to both the probe and Earth, we could maintain a shared pool of entanglement. Though the capsules themselves travel slowly, once the particles are in place and their link is established, they could be used to generate fresh encryption keys on demand, ensuring that any data packets sent back and forth at light speed would be utterly secure from interception for the entire multi-year journey. Quantum communication doesn't promise to break the speed of light, but it does promise to break the barriers of trust and security over the incomprehensible distances between the stars, weaving a web of unbreakable connection across the galaxy. While the magnetic sail proposes using a planet's magnetic field as a brake, another concept takes this idea of using the environment even further, literally using the sky itself to slow a spacecraft down. This technique is called Aerocapture, and it transforms a planet's atmosphere from an obstacle to avoid into a tool we can actively use. The principle is one of breathtaking audacity. Instead of firing a rocket engine to slow down for orbital insertion, a maneuver that consumes a massive amount of precious fuel, a spacecraft deliberately dips into the outer fringes of a planet's atmosphere. The sheer friction and drag against the spacecraft's specially designed heat shield act as a natural brake, sapping away its immense orbital velocity in one thrilling, controlled dive. It's the ultimate cosmic maneuver, trading speed for heat and emerging on the other side slowed down and ready for orbit, all without a single drop of propellant being burned. This idea was first seriously proposed for missions to Mars, where the savings would be most dramatic. The challenge of getting a heavy scientific payload into orbit around the red planet is immense. Without Aerocapture, nearly half of a spacecraft's mass at arrival might need to be dedicated to fuel just for the braking burn. For decades, however, mission planners considered the technique far too risky to attempt with a billion-dollar mission. The concerns were numerous and terrifyingly valid. Could a heat shield be designed to withstand the intense and prolonged heating of skimming through an atmosphere at interplanetary speeds? Could navigation be precise enough to ensure the spacecraft dipped to exactly the right depth too shallow, and it would skip back out into space without slowing down too deep, and it would burn up or break apart from the incredible forces? The margin for error was vanishingly small, and the consequence of a mistake was total mission loss. As a result, Aerocapture remained a fascinating theoretical concept discussed in research papers, but deemed too dangerous for real-world application. The validation of this once-rejected idea has been a story of incremental courage and technological triumph, largely written by the robotic pioneers we've sent to Mars. While not a pure Aerocapture, the missions that laid the groundwork were the atmospheric entries of the Mars rovers. Each one, from Pathfinder and Spirit and Opportunity to the monumental Curiosity and Perseverance landings, performed a maneuver called aerobraking, using the atmosphere to slow down significantly, but still relying on final rocket burns for the last steps. These missions were masterclasses in precision-guided entry, descent, and landing, proving we could navigate a spacecraft through the Martian atmosphere with astonishing accuracy. More importantly, they served as real-world tests for advanced heat shield materials like pica, the phenolic-impregnated carbon ablator, which was proven capable of surviving the hellish conditions of atmospheric entry. The success of these missions provided the crucial confidence and data needed to finally green-light true Aerocapture. The advances that have sealed the deal are happening on multiple fronts. Material science has delivered new generations of lightweight, ultra-resilient thermal protection systems that can handle higher temperatures for longer durations. Perhaps even more critical has been the revolution in guidance, navigation, and control systems. Modern spacecraft can now autonomously adjust their angle of attack in real time during the atmospheric dive, much like a surfer shifting their weight to ride a wave. This ability to ride the atmosphere, making tiny adjustments to control the drag and lift being generated, allows the spacecraft to steer itself towards the desired exit trajectory, compensating for unpredictable atmospheric densities and initial navigation errors. This transforms the maneuver from a passive, ballistic plunge into an active, pilotable flight through the sky of another world. The payoff for mastering this technique is a complete transformation of deep space mission architecture. By eliminating the need for heavy orbital insertion fuel, Aerocapture allows us to either send much larger, more capable scientific payloads to a destination for the same launch cost, or to use smaller, cheaper rockets to send the same payloads. This drastic reduction in mass and cost makes previously unthinkable missions not just possible, but practical. Aerocapture is now a cornerstone strategy for proposed missions to worlds with substantial atmospheres. At Venus, a spacecraft could use the planet's incredibly thick, soupy CO2 atmosphere to break into orbit, enabling long-term studies of its runaway greenhouse effect. At Saturn's moon Titan, a probe could aerocapture in its dense, nitrogen-rich atmosphere, opening the door to extended exploration of its methane lakes and probiotic chemistry. This technique effectively gives us a key to gently and efficiently unlock orbits around these fascinating worlds. Aerocapture represents a philosophical leap in how we explore. It signifies a shift from seeing the solar system as a series of obstacles to be overcome with sheer force, to viewing it as an environment filled with tools we can cleverly employ. We are learning to sail not on oceans, but on the atmospheres of other planets, using their very nature to aid in their own exploration. This elegant, fuel-free braking system doesn't just make missions cheaper, it makes them more frequent, more ambitious, and ultimately, more sustainable, paving the way for a future where slipping into the sky of an alien world is a standard, welcomed part of the journey. But what if the most efficient way to move through space wasn't to carry an engine at all, but to simply reach out and grab the momentum you need? This is the elegant promise of space tethers, a concept that turns the fundamental laws of orbital mechanics into a dynamic, reusable transportation network. The principle is a masterclass in cosmic cleverness, leveraging one simple, unbreakable rule. In orbit, energy and momentum are conserved. A momentum exchange tether operates like a celestial game of catch. Imagine two spacecraft connected by a long, strong cable, spinning around a common center of mass. A small, incoming payload approaches the system and is snagged by the fast-moving end of the tether. In the act of being caught, the payload steals a tiny bit of the tether system's momentum, slowing its rotation minutely. The payload, now moving much faster than it was before, is then released and flung like a stone from a sling onto a higher energy trajectory, all without expending any propellant. Conversely, a payload arriving from a higher orbit could be caught to transfer its excess momentum to the tether, boosting the system's rotation, which it could then use to fling the next payload even harder. It's a perpetual motion machine that obeys all the laws of physics, using nothing but momentum as its currency. For decades, this brilliant idea was relegated to the fringes of aerospace engineering, dismissed as a theoretical parlor trick too complex and fragile for the harsh reality of space. The litany of practical objections was long and, at the time, entirely valid. Could a cable kilometers long be deployed reliably without tangling or breaking? What material could possibly be strong and lightweight enough to withstand the incredible tensile forces and the constant threat of micrometeoroid impacts? The guidance and navigation required to have a spinning tether precisely capture a free-flying object moving at thousands of miles per hour seemed like an insurmountable challenge, a feat of coordination compared to catching a bullet with a thread. The risks of a failed capture attempt, a collision that could create a cloud of dangerous debris, were deemed too great. As a result, while physicists admired the elegant math, mission planners stuck with the known reliability of chemical thrusters, and the tether remained a fascinating footnote. The dramatic shift in fortune for this rejected concept is a story of incremental proof and entrepreneurial daring, led by companies like Tethers Unlimited. The first major step was proving that deployment itself was possible. Missions like the Small Expendable Deployer system have successfully unfurled tethers in orbit, demonstrating that kilometers of cable can be managed in microgravity. But the real breakthrough has been the miniaturization and democratization of space access. The rise of small satellites and CubeSats provided the perfect, low-risk platform to test these technologies. Tethers Unlimited, for instance, has flown multiple experiments, such as the multi-application survivable tether, designed to test the durability of tether materials against the space environment and prove they can generate useful current. Their electrodynamic debris eliminator, or ED, vehicle concept is a spacecraft designed to do nothing but sail on Earth's magnetic field using an electrodynamic tether, maneuvering itself to rendezvous with and deorbit dangerous space junk. These aren't just paper studies, they are active, funded projects moving from the lab to low Earth orbit, transforming the theoretical into the tangible. The potential applications for a mature tether technology are so vast they could redefine our entire infrastructure in space. The most immediate and critical use is in cleaning up the growing cloud of orbital debris. A tether-equipped spacecraft could gently capture a defunct satellite, and by either lowering its orbit to burn up or by using an electrodynamic tether to generate thrust against Earth's magnetic field, guide it to a safe disposal without any need for fuel. Looking further out, a network of momentum exchange tethers could act as a constant, reusable launch system. A payload launched from Earth on a small, cheap rocket could be caught by a tether in low orbit and flung to a higher orbit, to a space station, or even on a trajectory to the Moon. The next payload arriving from that high orbit would transfer its momentum back to the tether, re-energizing the system. This creates a propellantless shuttle service running on the natural energy differences between orbits, drastically reducing the cost and complexity of moving people and cargo around the Earth-Moon system. It's the foundational technology for a dynamic, interconnected orbital economy, turning the void of space into a place of constant, free-flowing motion. But if we can learn to sail on atmospheres and catch momentum with tethers, why not take the next logical step and simply move into the neighborhood? This brings us to a concept that redefines the very meaning of real estate in space: hollow asteroids. Envision a massive space rock, not just as a source of raw materials, but as a ready-made shell for a thriving colony. The process is one of cosmic-scale architecture. We would carefully select a stable, solid asteroid, then use advanced mining techniques to carefully excavate its interior, creating a vast, hollow cavity. This newly formed cavern would then be spun along its axis to generate artificial gravity on its inner surface through centrifugal force. The exterior, meters-thick shell of rock and regolith would provide near-perfect protection from cosmic radiation and solar flares, while the asteroid's own resources could be processed to create atmosphere, water, and building materials for the interior world. It's the ultimate act of cosmic recycling, transforming a lifeless rock into a shielded, self-sustaining habitat. This vision is far from new. It has been a beloved staple of science fiction for generations, most famously depicted in films and books where these hollowed-out worlds serve as bustling trading posts or secret military bases. Yet, for the better part of the 20th century, the idea was dismissed by engineers and scientists as a mining and construction fantasy of the highest order. The practical objections were immense and seemingly insurmountable. How do you spin an irregularly shaped rubble pile asteroid without it instantly flying apart under the centrifugal force? How do you excavate and reinforce millions of tons of rock in the airless, zero-gravity environment of space? The sheer scale of the engineering required, with no existing technology even remotely capable of beginning such a task, made the concept seem like a whimsical dream for a future thousands of years away, completely disconnected from the practical challenges of simply getting humans to Mars. The dramatic revival of this once fanciful idea is a direct result of the parallel progress we're making in two critical fields: asteroid mining and in situ resource utilization. The very companies and research programs dedicated to extracting resources from asteroids are, in effect, developing the exact toolkit needed to eventually hollow one out. They are pioneering the robotic excavators, the material processors, and the structural analysis techniques required to understand and manipulate these celestial bodies. Suddenly, the question is no longer if we can work an asteroid, but how and to what end. This shift in capability has forced a corresponding shift in imagination. Scientists and engineers are now seriously revisiting those old science fiction designs, running sophisticated computer models to determine the stability of different asteroid types when spun, and drawing up detailed blueprints for how to pressurize an interior cavity, how to line it with radiation-shielding water ice harvested from the asteroid itself, and how to create a self-contained biosphere within this most ancient of structures. The advantages of such an approach are staggering and fundamentally redefine the economics of space settlement. The single greatest cost in space construction is launching material from the deep gravity well of Earth. A hollowed asteroid habitat bypasses this problem entirely. The structure itself is already in space, and the primary building material, the rock of the asteroid, is available in virtually limitless quantities, right there on site. This makes it arguably the most scalable and sustainable model for large-scale space colonization ever conceived. These asteroids could serve a multitude of purposes. They could be towed into stable orbits to act as way stations and refueling depots on the interplanetary shipping lanes between Earth and Mars. They could become ideal research bases for long-term scientific studies, their thick walls offering unparalleled protection for sensitive experiments and their crews. Or, in their ultimate form, they could be transformed into permanent homes for thousands of people, with parks, towns, and farms laid out along the curving inner landscape, all under the glow of artificial sunlight streaming in from a central axis. This concept represents the final blurring of the line between exploration and settlement. It moves beyond the idea of simply visiting other worlds to the profound notion of literally building new worlds from the raw material of the cosmos itself. A hollow asteroid is more than a habitat. It is a testament to a future where humanity no longer just inhabits space, but actively shapes it, using the very bones of the solar system to create secure, sustainable, and expanding arcs for our species. It promises a future where our neighborhoods are not just on planets, but are planets themselves, small, mobile worlds of our own creation, carrying human civilization outward into the infinite frontier. Perhaps the most immediate and vital application for these powerful beams of focused energy lies not in reaching for the stars, but in protecting the world we already have. This brings us to the concept of directed energy weapons for planetary defense, a proposition that transforms tools often imagined for conflict into our planet's most sophisticated guardians. The underlying principle is one of elegant physics. Imagine a network of powerful space-based lasers focusing their energy onto a small, precise spot on the surface of an incoming asteroid. The intense heat doesn't need to blow the rock apart. Instead, it instantly vaporizes a tiny portion of its surface, creating a jet of superheated gas and plasma that erupts outward. Just like a miniature rocket engine, this plume of vaporized material pushes back against the asteroid, imparting a gentle but continuous thrust. Over months or even years, this subtle, persistent nudge, applied while the asteroid is still millions of miles away, would be enough to alter its trajectory ever so slightly, ensuring it safely misses Earth entirely. It's a method of cosmic deflection that relies on precision and patience over brute force, For the longest time, this idea was relegated to the realm of action movies and speculative fiction, dismissed by the scientific mainstream as a technically unworkable fantasy. The criticisms were formidable and, for their era, completely valid. The power requirements were deemed astronomical. To generate a laser beam powerful enough to vaporize rock across interplanetary distances would require a power source far beyond anything we could feasibly launch or build in space, making the entire concept seem like an energy-hungry pipe dream. Furthermore, the precision guidance needed to keep a laser locked on a specific, tumbling, irregularly shaped rock from such a vast distance was considered an insurmountable challenge. Critics also pointed to the potential for unintended consequences. What if the laser inadvertently fractured a loosely bound rubble pile asteroid, turning a single manageable threat into a deadly shotgun blast of debris still on a collision course? These overwhelming hurdles led most to conclude that while the physics was sound in theory, in practice, it was a hopelessly impractical solution. The dramatic shift in perspective, moving this idea from the fringe into serious scientific workshops and NASA studies, has been driven by two powerful forces: a sobering acknowledgement of the threat and a quiet revolution in laser technology. The first factor is our growing understanding that asteroid impacts are not a question of if, but when. Events like the Chelyabinsk meteor in 2013, which injured over 1,000 people with its airburst shockwave, served as a stark reminder that we are still vulnerable to cosmic bombardment. This growing awareness created a renewed urgency to develop viable deflection strategies beyond the theoretical. The second, and perhaps more crucial factor, has been the exponential advancement in laser efficiency and power. The development of fiber optic lasers and other solid-state technologies has dramatically increased the amount of coherent light we can generate per unit of electrical power, while simultaneously reducing the size and weight of the systems. We are no longer talking about building a Death Star. We are talking about deploying a scalable array of efficient, powerful, and focusable lasers that could work in concert. This new reality is best exemplified by the groundbreaking success of NASA's Double Asteroid Redirection Test, or DART mission. While DART used a kinetic impactor, a spacecraft crashing into an asteroid rather than a laser, its triumphant proof of concept in 2022 was a watershed moment for all planetary defense strategies. It demonstrated that we could indeed accurately intercept a small celestial body and measurably alter its orbit through a directed application of force. This success has opened the floodgates for serious research into the laser ablation alternative. Scientists are now conducting detailed laboratory experiments, firing lasers at asteroid analog materials to precisely measure the thrust generated by the resulting vapor plumes. Advanced computer models are simulating how different types of asteroids, solid rock, metallic, or loose rubble piles, would respond to such treatment, allowing engineers to design systems that would nudge rather than shatter. The conversation has decisively shifted from whether it could work to how we would best implement it. The most compelling vision for this technology is a permanent orbital sentinel network. This wouldn't be a single weapon, but a distributed constellation of solar-powered laser satellites stationed at gravitational sweet spots like the Lagrange points. These silent guardians would constantly survey the skies, and if a threatening object were detected on a potential collision course years or decades in the future, the network could activate. Multiple lasers would focus on the asteroid, their combined energy providing the steady, gentle push needed to gradually change its velocity by just a few centimeters per second, a tiny change that, over the vast distance of space, adds up to a miss of thousands of miles. The beauty of this system is its dual-use potential. The same powerful lasers designed to protect Earth could be repurposed during peacetime for entirely peaceful endeavors. They could provide propulsion for other spacecraft, pushing lightweight probes with laser sails on high-speed tours of the solar system. They could be used for precision mining of asteroids, slicing through rock or ice with incredible accuracy to process resources for future space colonies. This transforms the system from a planetary insurance policy into a multi-purpose tool for enabling our future in space. Ultimately, the story of directed energy planetary defense is one of the most powerful examples of a rejected idea finding its purpose. It highlights how technologies initially viewed through a narrow lens of conflict can be reimagined as instruments of preservation. It demonstrates our species' growing maturity, our ability to look up, identify an existential threat, and devise a clever, non-destructive solution using the fundamental laws of physics. This concept is a testament to human ingenuity turning our most powerful inventions toward the ultimate goal, safeguarding our shared home and all the life upon it, ensuring that our story continues for generations to come. Yet for all our ingenuity in building arcs and wielding lasers, the most intimate frontier of space travel remains the human body itself and the profound challenge of time. This brings us to a concept that has captivated storytellers for generations, one that promises to conquer the vast, empty eons between stars not with faster engines, but by essentially pausing the passenger, cryogenic sleep, or suspended animation. The principle is deceptively simple. By significantly lowering an astronaut's core body temperature and inducing a controlled, deep torpor state, their metabolic rate could be slowed to a tiny fraction of its normal pace. In this state, the body's demand for oxygen and nutrients would plummet, halting the aging process for the duration of the journey and eliminating the need for vast supplies of food, water, and air. A spacecraft wouldn't need to be a bustling generation ship. It could be a silent, efficient vessel carrying its dormant crew across centuries, awakening them only upon arrival at a new world, having experienced the multi-generational voyage as little more than a single night's sleep. For the vast majority of scientific history, this idea was dismissed out of hand as biological fantasy, a convenient narrative device for science fiction that bore no resemblance to medical reality. The obstacles were not just difficult, they were considered fundamentally insurmountable. The process of freezing a living, complex organism like a human being was understood to be catastrophically destructive. As water within cells freezes, it forms sharp, jagged ice crystals that act like microscopic shards of glass, shredding cell membranes and delicate tissues from the inside out. Even if freezing could be avoided, the profound cold itself would cause drastic biochemical shifts, shutting down essential organ functions and leading to irreversible brain damage and death. The scientific consensus was clear. A human body could be frozen, but it could not be frozen and then successfully revived. It was a one-way trip, making the concept useless for space travel and relegating it to the realm of pseudoscience and fringe cryonics movements focused on post-mortem preservation. The dramatic shift that has brought cryogenic sleep in from the cold, so to speak, is a story of medical research finding inspiration in the natural world and applying it to emergency medicine. Scientists began to look closely at animals that routinely undergo hibernation. A bear, for instance, can sleep for months without eating, drinking, or wasting away its muscle and bone mass. Its body temperature drops, its heart rate slows to a few beats per minute, and its metabolism adjusts to live off its own fat stores, all while protecting its brain and vital organs from damage. Researchers realized the goal wasn't to freeze astronauts, but to induce a similar, stable state of metabolic hibernation. This reframing of the problem from cryogenics to torpor was the critical breakthrough. Parallel research in emergency trauma medicine provided the next piece of the puzzle. Doctors discovered that inducing mild therapeutic hypothermia in patients after cardiac arrest or severe brain injury could dramatically improve survival rates and reduce neurological damage. By cooling the body, they were essentially slowing down the metabolic processes that cause cell death in oxygen-deprived tissues, buying precious time for treatment. This proved that a controlled, protective hypothermic state was not only possible in humans but could be medically beneficial. This convergence of biology and medicine has ignited a new wave of serious research, with space agencies and private companies leading the charge. NASA Advanced Concepts Institute has funded studies into torpor technology for spaceflight, not for interstellar journeys yet, but for the more near-term challenge of a 6 to 9 month trip to Mars. Their designs envision a crew module where astronauts spend the majority of the transit in a slumber state, monitored by automated medical systems and awakened only for brief periods. The advantages are immense. A hibernating crew would require far less space, food, water, and air, allowing for a much smaller, lighter, and cheaper spacecraft. Perhaps even more importantly, it would solve the twin scourges of long-duration spaceflight, radiation exposure, and psychological strain. By drastically reducing their metabolic activity, astronauts would theoretically be less vulnerable to the cell damage caused by cosmic rays. And by sleeping through the monotonous, confined journey, they would bypass the immense mental health challenges of isolation and confinement, arriving at Mars psychologically fresh and ready for the demanding work of exploration. Companies like SpaceX have openly expressed interest in this technology, recognizing its potential to be a game-changer for their ambitious plans for Mars colonization. While still in the experimental phase, the path forward is clear. Research is focused on perfecting the safe induction of torpor, likely through advanced pharmaceutical cocktails or targeted cooling techniques, rather than whole-body freezing. The focus is on stability, safety, and most crucially, reliable reversibility. The first human trials will almost certainly be for short-term medical applications here on Earth, gradually extending the duration as the science becomes more robust. The ultimate goal is a technology that doesn't just make long journeys tolerable, but makes them irrelevant to the human experience on board. Cryosleep invites us to reimagine the very nature of exploration, transforming a voyage that would once have been a grueling test of endurance into a peaceful passage, where the greatest challenge isn't surviving the journey, but simply closing your eyes in one world and opening them in another, ready to step into the future. But if we are to build a future among the stars, we will need an army of workers, and sending them from Earth is impractical. This brings us to a concept that is perhaps the ultimate expression of machine intelligence and autonomy: the self-replicating robot. The vision was first formally proposed by the multifaceted genius John von Neumann, who imagined what he called universal constructors. These wouldn't be simple robots, they would be complete automated factories, capable of landing on a distant world, using local materials to build more copies of themselves, and then sending those copies onward to repeat the process ad infinitum. A single probe could become 2, then 4, then 8, creating an exponentially growing network that could theoretically map every star system in the galaxy within a surprisingly short cosmic timescale, all without a single human ever leaving the solar system. For decades, this idea was less a proposal and more a cautionary tale, a theoretical nightmare scenario discussed more in the context of existential risk than exploration. The overwhelming fear was of a so-called grey goo apocalypse, where a single misprogrammed replicator would turn every planet, moon, and asteroid into nothing but more replicators, consuming the entire galaxy in a wave of mechanistic consumption. This terrifying potential, combined with the sheer mind-boggling complexity of designing a machine that could not only build itself but also find, process, and assemble raw materials in an utterly alien environment, led most scientists to dismiss von Neumann probes as a fascinating but dangerous thought experiment, one best left on the drawing board. The paradigm shift that has brought this concept in from the cold is the quiet, concurrent revolution in three separate fields: artificial intelligence, robotics, and additive manufacturing. We are now, for the first time, developing the components of a von Neumann probe, not as a single terrifying entity, but as a suite of practical tools. Advanced AI is providing the brain capable of making complex decisions and adapting to unforeseen problems. Robotics is creating the versatile hands needed to manipulate the environment. And most crucially, 3D printing is proving to be the foundational technology for the factory itself. We are already demonstrating the ability to use regolith, the dust on the Moon and Mars, as a printing medium to create structures, tools, and even spare parts. The leap from printing a wrench to printing the components of another printer is still vast, but it is no longer a leap of pure fantasy. It is a staggering engineering challenge we are actively beginning to unpack. This is why the first applications won't be for galactic conquest, but for local construction. Before we send humans on a years-long journey to Mars, we could send ahead a small fleet of highly specialized robots. Their mission would not be full self-replication, but a limited form of self-assembly and construction using in-situ resources. They could land, deploy solar panels for power, and then slowly but autonomously begin mining Martian soil and rock, processing it, and feeding it into massive 3D printers to build the landing pads, radiation-shielded habitats, and greenhouses that human pioneers will need upon their arrival. This changes the entire mission architecture from camping to moving into a prepared home, drastically reducing risk and cost. The ethical considerations here are profound and cannot be an afterthought. The moment we grant a machine the capability to create copies of itself, we must install absolute, unbreachable safeguards. These would likely include strict limits on the number of generations it can replicate, a built-in shutdown command that responds to a specific signal from Earth, and a geographical limitation, perhaps confining its activities to a single celestial body. The goal is to create a tool, not a new form of life with its own agenda. The promise, however, is nothing less than the automation of the entire space industry. A successful von Neumann probe, even in a limited form, would be the ultimate force multiplier. It would allow us to build an entire infrastructure on a world without ever lifting another shovel of earthly material into orbit. It is the key that unlocks the solar system, turning scarcity into abundance through the power of automated, sustainable creation. But what if the most promising world for human settlement isn't the red plains of Mars or the airless Moon, but the toxic, crushing hellscape of Venus? It sounds like a paradox, yet this is the brilliant, counterintuitive logic behind the concept of orbital cloud cities. While the surface of Venus is a textbook example of a planetary inferno, with temperatures hot enough to melt lead and pressures equivalent to being a mile underwater, a remarkable transformation occurs about 30 miles up in its thick carbon dioxide atmosphere. At this precise altitude, the atmospheric pressure is nearly identical to Earth's at sea level, and the temperature ranges between 0 and 50 degrees Celsius, a perfectly comfortable shirt-sleeve environment. Here, in this unexpected sweet spot, a human wouldn't need a massively pressurized suit. they would need only an oxygen mask and protection from the sulfuric acid clouds. It's a layer of almost Earth-like normality suspended in the most unlikely of places. The idea of building a city to float permanently in this alien sky was, for a very long time, the stuff of pure science fiction, a whimsical notion dismissed by pragmatic aerospace engineers. The challenges seemed designed to inspire despair. How do you construct a habitat that can resist the corrosive effects of sulfuric acid mist? What material could possibly be both lightweight and durable enough to contain a breathable atmosphere while floating indefinitely? The concept of a balloon-based colony was often met with a chuckle and a comparison to the fantastical floating city of Laputa from Gulliver's Travels, a charming story, but not a serious architectural blueprint. The overwhelming consensus was that if we were to build a home away from home, it would be on solid, familiar ground, not drifting through the corrosive clouds of a planetary nightmare. This dismissal began to crumble under the weight of serious scientific analysis, most notably from NASA itself. The space agency's high-altitude Venus operational concept, or HAVOC, study was a landmark moment. This wasn't a speculative paper from a fringe group. It was a detailed engineering assessment from one of the world's leading space institutions. The HAVOC design proposed a magnificent vision, a massive, rigid dirigible filled with a breathable gas like oxygen and nitrogen, which would be lighter than the dense carbon dioxide atmosphere of Venus and therefore naturally buoyant. This mothership would serve as a base of operations, with smaller robotic and eventually crewed vehicles deployed from it. The study meticulously addressed the previous objections, pointing out that the sulfuric acid corrosion is a manageable engineering problem, solvable with modern Teflon-like coatings or other inert materials. Furthermore, Venus's upper atmosphere offers two tremendous resources: abundant solar power, as the cloud layer is above much of the light-blocking haze, and a ready-made source of buffer gas for the airships, as the CO2 atmosphere itself could be processed. The renewed vigor for this concept is also being driven by a new generation of private ventures and a shifting perspective on what colonization means. Rather than seeing Venus's atmosphere as a hostile barrier, pioneers are now viewing it as a vast, unexplored ocean, a new medium to be sailed. The parallels to maritime exploration are striking. We wouldn't try to live on the ocean floor, we'd build ships to sail its surface. In the same way, a cloud city isn't trying to conquer the hellish surface of Venus. It is elegantly skipping over that problem entirely to inhabit the benign ocean of air above it. This approach offers a unique advantage over Mars colonization. The gravity at that altitude is about 90% of Earth's, eliminating the debilitating health effects of long-term exposure to low gravity. A child could grow up there strong-boned and healthy, a prospect that remains a significant challenge on Mars. The potential life cycle of such a settlement is a story of increasing ambition. The first phase would be a robotic scout, a proof-of-concept aerostat that could operate for months, analyzing wind patterns and environmental conditions. This would be followed by a manned mission, perhaps lasting 30 days, where astronauts would live and work in the dirigible, proving the technologies for long-term habitation. The final, breathtaking phase would be the establishment of a permanent colony, likely starting as a series of interconnected modules forming a larger station. These cloud cities could eventually become self-sustaining. The atmosphere is rich in carbon, oxygen, and sulfur, all the basic building blocks needed to produce water, air, and even construction materials. They could become scientific paradises, studying Venus's runaway greenhouse effect as a stark warning for Earth's climate future, or serve as way stations for deeper solar system exploration. This vision transforms Venus from a planetary dead end into a potential archipelago of floating human outposts, proving that sometimes the most viable path to a new world isn't down to its surface, but up into its sky. Yet, even as we master the art of riding magnetic fields and sculpting asteroids, some of the most profound breakthroughs are emerging from a radically different approach, one that manipulates light itself not as a blunt force, but with the precision of a master craftsman. This brings us to the photonic laser thruster, a concept that sounds like it defies its own logic. How can light, which has no mass, be used to create thrust, and how could that possibly be efficient? The answer lies in a brilliant piece of physics ingenuity that recycles its own power. Imagine a standard laser, but its beam is not fired once into the void. Instead, it is trapped between two mirrors, forming an optical cavity where a single photon can bounce back and forth thousands of times before it is finally absorbed or escapes. Each time that photon reflects off a surface, it imparts a tiny amount of momentum. A conventional laser sail gets one push per photon. A photonic thruster, by cleverly trapping light, can get the same photon to push not once, but thousands of times, multiplying its effective force by orders of magnitude and achieving a theoretical efficiency that begins to make laser propulsion a practical reality for delicate tasks. This idea was initially met with deep skepticism, not because the physics was wrong, but because the engineering challenges seemed designed to overwhelm any potential benefit. The primary obstacle was loss. In any real-world system, each bounce of the photon within the cavity would lose a minuscule amount of energy to imperfections in the mirrors or absorption. Critics argued that these losses would quickly accumulate, sapping the system of any net gain and making the entire recycling concept pointless. The precision required was also staggering, maintaining the perfect alignment of an optical cavity between a spacecraft and a distant laser source, while both are moving at incredible speeds, was considered an impossible feat of coordination, a solution in search of a problem that could be more easily solved with a tiny puff of traditional chemical propellant. The turning point for this dismissed concept arrived not with a single grand experiment, but through the persistent, incremental work of researchers determined to prove the math could work in practice. The pioneering work of Dr. Young B at the B Institute demonstrated this principle in a landmark laboratory experiment. Using an optical cavity with incredibly high-quality, low-loss mirrors, his team was able to measure a small but definitive thrust from this recycled light, proving that the amplification effect was real and could overcome system inefficiencies. This wasn't a full-scale propulsion system, but it was the crucial proof of concept that shattered the old assumptions. NASA's Innovative Advanced Concepts program took notice, funding further research into the technology, recognizing its potential for a specific, critical niche, ultra-precise station keeping and formation flying. The most compelling applications for photonic thrusters are in missions where flawless precision is more important than raw power. Consider a future array of space telescopes, like a successor to the James Webb, but consisting of multiple individual mirrors flying in perfect formation to act as one giant observatory. Maintaining that exact alignment, where even a millimeter of drift could ruin the focus, is a task far too delicate for conventional thrusters, which produce minuscule but unpredictable plumes of gas. A photonic thruster, by contrast, could provide a continuous, whisper-fine, and perfectly measurable force, nudging each component with the gentleness of a photon's touch. This same precision makes it an ideal technology for tackling the growing crisis of space debris. A small satellite equipped with a photonic thruster could safely rendezvous with a defunct piece of junk, and by directing its laser beam at it, gently push it into a decaying orbit without any physical contact, avoiding the risk of creating more debris through a collision. It transforms a laser from a destructive beam into a tool of delicate orbital stewardship. This technology exemplifies a broader and incredibly important theme in advanced propulsion: the move from brute force to elegant efficiency. It's not about building a bigger engine, it's about building a smarter one, by focusing on amplifying the effect of every single particle of light. The photonic thruster turns a fundamental limitation of light-based propulsion, its weakness, into its greatest strength for applications requiring supreme control. It suggests a future where the intricate ballet of satellites in Earth orbit and the precise alignment of deep space observatories are managed not with explosive chemical reactions, but with the silent, sustainable, and infinitely controllable pressure of recycled light. But what if the greatest value of space isn't just in the resources we find there, but in the unique conditions it offers for building things we simply cannot create on Earth? This is the revolutionary promise of space-based manufacturing, a concept that reimagines the orbital environment not as a void to be crossed, but as the ultimate workshop. The magic ingredient is microgravity. Down here on Earth, gravity is a constant, tyrannical force that shapes every industrial process. It causes denser materials to sink and lighter ones to float. It creates convection currents that disrupt delicate chemical reactions, and it exerts stress on fragile structures during their formation. But in the persistent free fall of orbit, that force is virtually eliminated. This allows for the creation of products with a perfection and uniformity that are literally impossible to achieve under the influence of Earth's pull. From flawless crystal lattices for semiconductors to incredibly pure fiber optics and even complex, three-dimensional human tissues. The vision of orbital factories is far from new. NASA and other agencies have been conducting microgravity experiments since the Skylab missions of the 1970s, and the idea of commercial manufacturing took hold in the 1980s during the early days of the Space Shuttle program. Companies like 3M and McDonnell Douglas flew experiments to develop new drugs and materials, envisioning a near future where the shuttle would regularly ferry payloads to and from a thriving industrial park in orbit. Yet for decades, this dream was consistently grounded by one overwhelming, undeniable obstacle: the astronomical cost of launch. It simply made no economic sense to build a factory in space when the price of sending the raw materials up and bringing the finished products back down was measured in thousands of dollars per pound. The business models were untenable, and the concept was largely dismissed as a subsidized fantasy, a solution in search of a problem that didn't justify its own exorbitant price tag. The catalyst that has utterly transformed this rejected idea is the same one revolutionizing so many other aspects of spaceflight: the dramatic reduction in launch costs driven by private companies like SpaceX and their reusable rockets. By slashing the price of access to orbit, they have fundamentally rewritten the economic equation for in-space production. Suddenly, it became feasible to consider manufacturing items in space that are incredibly valuable by weight. This economic shift coincided with a crucial change in infrastructure. The International Space Station opened its doors as a national laboratory, hosting commercial experiment modules from companies like NanoRacks and offering them a ready-made, crew-tended platform to test their technologies. This provided the low-risk, accessible proving ground that the nascent industry desperately needed. We are now witnessing the very first chapters of this new industrial revolution being written. Companies are already up there right now producing tangible value. For instance, a company called Varda Space Industries is focused on manufacturing pharmaceuticals in orbit. They have successfully crystallized proteins in microgravity that hold the potential for more effective HIV and cancer treatments, structures too large and complex to form perfectly on Earth. Another firm, fiber optic manufacturing in space, is producing a special type of glass called Z-blan. When drawn into fiber in 0G, it demonstrates significantly less signal loss than Earth-made versions, which could lead to a dramatic leap in the speed and efficiency of global data networks. Perhaps most astonishingly, bioprinting companies are using the ISS's microgravity environment to successfully print living human tissues and even miniature organs. Without gravity pulling down on the delicate, gel-like bioinks, these structures can maintain their complex three-dimensional shapes, offering scientists unprecedented models for drug testing and bringing us closer to the day of printing transplantable organs on demand. The long-term vision extends far beyond the confines of the ISS. The next logical step is the development of dedicated, free-flying orbital factories. These automated or remotely operated stations would be designed for specific, high-throughput manufacturing processes, free from the constraints of a crude laboratory. They could be supplied with raw materials mined from asteroids or the Moon, further reducing dependence on Earth. The products from these orbital factories would serve two booming markets: customers back on Earth, who will pay a premium for these uniquely perfect materials, and the future space economy itself. Imagine a construction depot at a lunar Lagrange point that uses metals processed from asteroid ore and 3D printed in microgravity to build massive spacecraft for missions to Mars, ships that could never be launched from Earth in one piece due to their size. This isn't just about making a few exotic products. It's about building an entire industrial supply chain in space for space. The economic implications of this shift are staggering. Analysts project that space-based manufacturing could grow into a multi-billion-dollar sector within the next few decades, creating entirely new markets and disrupting existing ones. It represents the moment we stop thinking of space solely as a destination for exploration and begin to see it for what it truly is: the ultimate high-tech workshop, a place where the very laws of physics are different, offering us a unique advantage to build a better future, both for those of us on Earth and for the generations that will one day call the stars their home. But if we are to truly become an interstellar species, our ambitions must eventually extend beyond the solar system and confront the ultimate energy source in the universe, the black hole. This brings us to our final concept, perhaps the most extreme and mind-bending of them all: black hole propulsion, a system that doesn't just use fuel, but seeks to harness the very fabric of spacetime twisted into a singularity. The underlying principles sound like they are pulled from the most daring realms of theoretical physics, because they are. One method, first proposed by the Nobel laureate Roger Penrose, is known as the Penrose process. It exploits the incredible properties of a rotating Kerr black hole. Surrounding such a monster is a region called the ergosphere, where spacetime itself is dragged around at relativistic speeds by the black hole's spin. Penrose calculated that if an object were to enter this ergosphere and split in two, with one half falling past the event horizon and the other escaping, the escaping fragment could actually emerge with more energy than the original object entered with. The black hole itself would lose a corresponding amount of rotational energy, effectively acting as a cosmic battery that we could tap into. Another, even more speculative idea involves not a massive celestial black hole, but a microscopic, artificial one. The concept here relies on the work of another legendary physicist, Stephen Hawking. According to his theories, black holes are not entirely black. They should emit a faint glow of thermal radiation, now called Hawking radiation, due to quantum effects at their event horizons. For a stellar mass black hole, this radiation is negligible, far colder than the cosmic microwave background. But for a tiny micro-black hole, perhaps one with the mass of a small mountain compressed into a size smaller than an atom, the story is completely different. Its Hawking radiation would be incredibly intense, a roaring outpouring of energy and particles as it evaporates. The proposal is to create, or more feasibly, to capture such a micro-black hole and feed it. By constantly supplying it with matter, perhaps in the form of stray hydrogen atoms collected from the interstellar medium, we could maintain it at a stable size, and the phenomenal energy of its Hawking radiation could be harnessed as exhaust for a starship, providing near limitless power. For the vast majority of the space age, these ideas were the exclusive domain of theoretical physicists scribbling on blackboards, concepts dismissed not because the math was wrong, but because the engineering and existential risks were so overwhelmingly terrifying. The Penrose process requires navigating the violent maelstrom just outside a black hole's point of no return, a feat of precision that seems ludicrously beyond any conceivable technology. The micro-black hole engine, however, presents a different kind of problem. How do you safely create and, more importantly, contain an object that has the mass of a mountain and the gravitational appetite of a singularity? A single malfunction, a breach in its magnetic or gravitational confinement, could result in the black hole falling into the heart of the spacecraft and eventually the planet itself, consuming everything. The sheer, apocalyptic danger of the technology led most to dismiss it as the ultimate in irresponsible science fiction, a power source whose potential for catastrophe made even nuclear pulse propulsion seem tame by comparison. What has kept this idea on the farthest fringes of scientific discussion is the relentless forward march of our understanding of quantum gravity and high-energy physics. While we are nowhere near creating a black hole, experiments at the Large Hadron Collider have, for the first time, allowed us to probe the energy regimes and conditions where the mathematics governing such objects becomes relevant. Furthermore, the detailed study of Hawking radiation, once a purely theoretical exercise, is now a vibrant field of research, with physicists proposing laboratory experiments using analogs like sonic black holes to observe similar effects. This ongoing research doesn't bring us closer to building an engine, but it does solidify the underlying physics from pure speculation into a robust, if distant, theoretical possibility. The conversation has subtly shifted from, "Is this magic?" to, "Could this ever be engineering?" The potential payoff for a civilization that could master such a technology is nothing less than dominion over the energy needs of interstellar travel. A Hawking radiation drive would be the ultimate energy-to-mass converter, dwarfing the efficiency of fusion or antimatter. It could accelerate a starship to a significant fraction of light speed and sustain that velocity for years, enabling journeys across the galaxy within a human lifetime. It represents the absolute extreme frontier of energy science, a point where power generation and fundamental physics become one and the same. To harness a black hole is to literally play with the most powerful forces in creation, bending the rules of the universe to our will. It is the ultimate testament to human curiosity and ambition, a challenge that asks if we are destined to forever be prisoners of the energy limits of our world, or if we can one day learn to tap into the engines that power the cosmos itself. From solar sails riding beams of light to the mind-bending potential of black hole propulsion, the journey through these 24 once-rejected concepts reveals a powerful and repeating truth about human progress. Innovation rarely begins with a quiet consensus. It often erupts from the edges of our imagination, from ideas so bold and unusual that they are initially met with dismissal, laughter, or outright disbelief. What unites these visionary concepts is not that they were proven wrong, but that the world simply wasn't ready for them yet. They existed ahead of their time, waiting for the twin engines of technological advancement and a shift in human perspective to finally catch up and propel them into the realm of possibility. This pattern tells us something crucial about the nature of discovery. The future is not a predetermined path we simply walk down. It is a landscape we actively build, and its blueprints are often first sketched in the margins of conventional thinking. The reusable rocket, the space elevator, the orbital ring, each was once a fantasy confined to the pages of science fiction. Today, they are subjects of serious research, funded projects, and concrete engineering plans. They teach us that the line between impossible and inevitable is not fixed. It is a horizon that continuously recedes before us, pushed back by our relentless curiosity and ingenuity. The greatest limitation we face is rarely the laws of physics themselves, but our own temporary inability to see how they might be harnessed. This evolution from fantasy to reality is accelerating at a breathtaking pace. The driving forces are clear: the plummeting cost of access to space, the rise of a vibrant private space industry, and breakthroughs in materials science, artificial intelligence, and quantum computing. These advancements are providing us with the tools to finally tackle those monumental engineering challenges that once seemed insurmountable. We are no longer just dreaming about these concepts. We are prototyping them, testing them in orbit, and writing the first lines of code for the algorithms that will one day guide them. The conversation has decisively shifted from "can it be done" to "how will we do it" and "when." Ultimately, this journey invites us to adopt a new perspective on ambition itself. It encourages us to look at the problems that define our era: climate change, resource scarcity, our confinement to a single planet, not as dead ends, but as invitations to think bigger. The solutions to our greatest challenges may not lie in incremental improvements to existing technologies, but in embracing the radical, the unusual, and the once rejected. The next chapter of our story will be written by those who dare to question the status quo, who are willing to be misunderstood in the short term in service of a long-term vision that stretches to the stars. So the next time you hear an idea that sounds too strange, too audacious, or too far-fetched to ever work, remember the solar sail, the magnetic brake, and the cloud city. Remember that the future belongs to the curious, the persistent, and the brave. It is built by those who are not afraid to ask "what if?" and then dedicate themselves to finding out. Who knows, the concept that everyone is dismissing today might be the very one that defines our tomorrow. If you've enjoyed this tour of the ideas shaping our future, be sure to like this video, subscribe for more journeys to the edge of what's possible, and let us know in the comments which of these 24 concepts you find